Okay, so good morning, everyone, and welcome to this webinar. I'm Pelagie, and I have taken over Pascal activities. So now I'm the EUPEX dissemination leader. So we are all here for a webinar. Today's webinar is on ParaStation Modulo Suite, a software solution developed to manage heterogeneous resources on HPC cluster at scale. But before into diving in this subject, just let me tell you that this EUPEX webinar is a series. We are doing monthly webinar to share results and lessons learned during the project. So we mainly present applications that we have analyzed and optimized under the project, and we can also share tools and the component of the EUPEX software stack. So all our webinars are recorded and are shared on our website and on our YouTube channel. You can find them on the link here. I will put it in the chat anyway. And we have one more webinar scheduled the 4th June. It will be on Ocean, an administration software stack developed by the CEA for HPC cluster administration. So yes. Now let's move on to our 6th webinar. It will be dedicated to ParaStation Modulo Suite. So this ParaStation is included in the EUPEX software stack and enables efficient management of large-scale heterogeneous HPC system. I'm very happy to welcome Simon Picard from ParTec. Thank you so much for accepting to be here and for sharing your insight about ParaStation Modulo. So Simon is leading the system software development at ParTec AG, and he's an expert on modular HPC and dynamic resource management. I will stop sharing my screen and I will let you share your screen, Simon.
Okay. So thanks, Pelagie, for the introduction. So hi, I'm Simon Picard, working at ParTec and heading the software architecture and development group. This is all about the further development of the ParaStation Modulo Software Suite in the context of the dynamic modular system architecture, which I will present to you in the following. I hope you can see my screen. If not, please.
Yes, we can.
Okay, perfect. Just a short introduction to ParaStation and ParTec in general. So we've been pioneering the dynamic modular supercomputing or system architecture, dMSA, for now more than 10 years in the context of various different nationally and European funded research projects, but also in co-design activities in customer projects. On the right-hand side, you see a bunch of different project logos that have been involved and helped shaping both the dMSA and ParaStation Modulo. So to name just a few of them, the C family of projects with DeepC, IOC, and RedC, of course, but also quantum-related projects like QSolid, HPCQS, of course, EUPEX, as we are currently in a EUPEX webinar, and finally, we will continue to do so in the upcoming projects like Darren Synergies. Here's an overview of ParaStation Modulo and its main components. So you can roughly divide it in 4 main parts. So going from the left-hand side, we have the ParaStation cluster tools, which are our Swiss Army knives for provisioning and managing large-scale heterogeneous modular systems. We have the ParaStation Health Checker, which enables us to ensure node integrity across the whole system and tightly integrates also with cluster tools. We have the ParaStation Ticket Suite, which is our solution as a central information hub for all parties involved setting up such a system, for routing triage, documenting things, planning maintenance, and so on. And finally, our execution environment and runtime library in terms of the ParaStation MPI part, which provides us with the MPI 4.1 compliant MPI library and supports various aspects of resource and process management, like full Slurm integration, a PMX server, and of course, support for modularity. Here you see an overview of how ParaStation Modulo integrates into our software stack for exascale. So as you can see, it plays a central part in the overall software stack. We sit on top of the OS layer and the control plane. So ParaStation Modulo requires, let's say, common Linux distribution. Usually we use something which is Red Hat Linux Enterprise based, and on top of that, our tools and solutions for managing large-scale heterogeneous systems sit on top. And we, of course, also integrate with external components such as monitoring system, orchestration systems, energy management, and so on. The main idea is that we provide a cluster management solution which allows us to provide the service and support people to have a unique interface to different components or system parts, even from different vendors or hardware types. We are also agnostic with respect to the underlying control plane, meaning that ParaStation Modulo can sit on top of classical HA setups or high availability setups, but of course also can be integrated in more modern cluster-based environments such as Kubernetes, but even also virtual machine-based control planes. The idea is that especially the ParaStation cluster tools, but also the other components hide away the differences between the different hardware modules so that we have a coherent interface that people on the service and support side can interact with the system, but also on the user level side allows users to run jobs across a system providing different modules with a unique interface and a unique view onto this heterogeneous hardware. And our goal is always to customize our solution to the needs of the customers and the computing sites so that we further develop and co-develop in a co-design fashion our software solution and tailor it to the requirements of the respective system. First of all, I would like to give you an overview of the idea behind modular supercomputing. So going back a bit in time, when we started to integrate heterogeneity into HPC systems, what would we do? We simply augmented the existing, usually CPU-based computing nodes by accelerator devices, such as GPUs, for example. This is the classical, let's say, fat node concept, where you have a static assignment between the number of accelerator devices in a compute node and the classical compute resources. The idea behind the modular supercomputing architecture or modular system architecture is to rather define the heterogeneity on the system level, meaning that we aggregate a resource type of similar characteristics like classical compute resources or accelerator resources in so-called modules. And back then we started, first of all, with the concept of the so-called cluster booster concept, which means that we have a cluster module, which more or less represents what we had back then in time when there were no accelerator resources yet available, and a booster module, which was specially intended for running the, let's say, scaling code parts of large-scale simulations usually benefiting from accelerator devices like GPUs. Especially to note is that the goal, of course, is to provide the user still with a coherent view onto the system, so that the user is able to run, for example, MPI session across both modules in a transparent way and does not have to deal with the fact that the system which is underlying is composed of different modules. In the same sense, we do not only support with this concept a coherent or unified network landscape, but if you consider that there might be situations where one hardware type would benefit from a certain network architecture compared to the other one, we would also support heterogeneous network landscapes within such systems, meaning that we have a federation in those systems, translating from the one network to the other, also in a transparent way. But this is not necessarily the case, of course. Both approaches are possible, but that is very important to mention that we are not limited here. And let's say if we already have the idea of aggregating resources into so-called modules, starting with the cluster and booster module, the next natural step is to think about what additional type of resources could we start to integrate into such a system. And this is then the dynamic modular system architecture or supercomputing architecture as we know it now, adding different kind of modules like a storage module, data analytics module, but even also other hardware types like a quantum module, for example, where we also work on solutions to integrate quantum computing devices into the dMSA in order to support their efficient utilization also in the HPC landscape. And the main idea behind this concept is that we believe it increases the efficiency of the overall system. So we do not anymore have the problem of the so-called dark silicon. So as I mentioned before, in previous times, we had a static assignment between the accelerator devices and the classical compute devices. But now the applications and workloads running on such a system can mix and match the available resources with the actual requirements of the system and optimize basically the mapping of the application to the different hardware types. Additionally, the modular supercomputing architecture allows us for an easy extensibility of the system in terms of adding new modules, but also upgradability, meaning that if one of the modules reaches its end of life, that does not necessarily mean that all of the modules have to be decommissioned, but we can simply update individual modules one at a time, but leave the overall system running. And finally, we believe that this approach leads us to a better scalability in an overall sense, since it allows applications and workflows for a better effective resource sharing and cost-effective scaling. Of course, what I presented until now is, let's say, the ideal world, meaning that we are able to put hardware resources of the same characteristics in so-called modules, but we all know that there are hardware architectures out there which do not fit this approach to 100%. And therefore, of course, this paradigm for designing systems is not limited to such kind of hardware architectures, but we would, of course, also support integrated architectures. So meaning that we might think about a solution where we have a highly integrated module, which features both classical compute and accelerator resources, but perhaps also an additional general purpose module, which has some other characteristics with respect to the classical compute resources, for example, featuring a higher memory bandwidth, for example. And of course, we then have to think about how to still make use of this efficient resource sharing, especially to avoid the problem of so-called dark silicon. And here, one solution is, of course, the possibility of doing efficient co-scaling of applications. And in this context, also the concept of malleability is of major interest, which I will show later on. So this was a quick overview of the ideas behind the dynamic modular system architecture. And now I would like to introduce to you the individual components of the ParaStation Modulo Software Suite, which is actually enabling systems following this paradigm for designing supercomputing systems. Starting first of all with the ParaStation cluster tools. As I mentioned before, this is our Swiss Army knife for the service and support people during their day-to-day work, like doing maintaincing, bootstrapping the system, updating, and so on. And it also integrates with our other components that I will introduce in the following, such as the health checker, but also the ticket suite to automatically create tickets if issues are detected, to react on results provided by the health checker, and so on. Then we have the ParaStation Health Checker. As I mentioned before, this is our tool that ensures integrity of the computing nodes, but also other components in the system in order to maximize the likelihood that computing nodes which are assigned to a certain job will also survive this job. In terms of that, we minimize the likelihood of any node failures during job execution. The health checker is mainly composed of two components. So on the one hand, we have the expandable framework, which allows us to define different tests and checks and their dependencies to a certain extent. And the second component is the so-called checkbot, which is an assistant that allows us to do regular additional checks of the computing nodes. For example, if they have been taken offline, some hardware repair has been done, then the checkbot will automatically iterate over those nodes and see if they can be brought back to production, for example, in order to further optimize the maintenance of the system and even further improve the overall utilization and also availability of the computing node. The main task of the health checker is to assess the health of the hardware components, the software components, but also, of course, the configuration. So if we think about a large-scale computing system, which features thousands of different components, we of course have to ensure that the configuration of the computing nodes, which are assigned to a certain job, match to each other so that we don't have any differences in configuration. And the goal is, of course, to maximize, again, the usability by so-called non-destructive testing. How do we achieve this? As we have basically two scenarios. So on the one hand, on trigger, and on the other hand, periodically. So periodically is what the checkbot basically does. And on trigger is that we integrate the ParaStation Health Checker, for example, with the prologue and epilogue phase of the resource management system, meaning that we run a certain amount of small tests and checks on the compute nodes just before a job is being executed. And at the end of the job, the health checker will be executed again to run some additional checks, but also cleanup actions, which could not be fulfilled by the runtime or the execution environment. This approach allows us to basically have an infinite scalability, since those checks are usually node local checks, meaning that we can execute them concurrently on all nodes which are assigned to a certain job. And this, of course, increases the efficiency of the solution. We have still different scopes of tests. So we have those local tests, like detecting are all CPUs available that we expect, the available memory, configuration, as I mentioned before. But there are also some remote tests depending on the configuration. So for example, if a node has been taken offline due to some hardware repairment or so on, then we would be able to run some more extensive testing with the health checker, also covering things like network throughput and so on and so forth. Oops. The third component is the ParaStation Ticket Suite, which is our solution for providing a central information hub to all parties that are involved in setting up a computing system, but also running and maintaining it during its lifetime. So the idea is behind the Ticket Suite that we provided to the customer, meaning that this is basically one of the first components that has been deployed at the customer side, so that we can start interacting through this ticket suite during already the setup phase of a system. But once the system has been installed, acceptance has been done, then of course the ParaStation Ticket Suite continues to serve as a vehicle for exchange between us, the hardware vendors, but also the customer side and hosting sides. Currently, we use the so-called truck system, which is also the solution that we have deployed in the context of the EUPEX project for the EUPEX Early Access Program. But we are currently also working on an integration with the a bit more modern GitLab platform, which will be available soon. But the idea is always the same, that we bring the ticket system as a solution to the customer side and dedicate it to a certain supercomputing system. And our fourth and final component is ParaStation MPI, which is in turn divided into two main parts. So on the one hand, we have the ParaStation MPI execution environment, which provides us with daemons used for resource and process management on the computing nodes. And on the other hand, the ParaStation MPI runtime environment library, which provides us with MPI 4.1 compatibility, and which is an MPICH-based derivative. First of all, the process and resource management. So what we do with the ParaStation, so-called ParaStation management daemons, is that we deploy one daemon per computing node and fully replace the management daemons provided by the scheduling solution, which is currently mostly Slurm in our setups. So what this means, as you can see here in this picture, is that we completely replace the Slurm daemon and Slurm step daemon, which are usually executed on the compute nodes, with our ParaStation management daemon, which are then talking to the Slurm components, like the user level tools like sbatch, srun, srlog, but also the Slurm control daemon, the native Slurm protocol. So we implement the native Slurm protocol with our ParaStation management daemon, and in turn provide capabilities which allows us to optimize and also customize the solution to the customer's needs, meaning that we might be able to implement different pinning strategies with respect to GPU and CPU resources. We have a very efficient and mature network of daemons, meaning that the protocol that is used to interact among those daemons is a self-development which provides us with very good scalability, and as we will also see in some later slides, which we even use to accelerate the startup of MPI applications to further improve the efficiency there. This is actually the point. So we leverage the ParaStation daemons to have a more scalable MPI in it. To understand that, what you need to know is that usually you need some kind of out-of-band communication when setting up an MPI communication session. So once the MPI communication session has been set up, usually the processes are talking over some kind of high performance interconnect and also corresponding protocol. such as InfiniBand verbs or some higher layer protocol. But in order to be able to set up this connection, we usually leverage classical Ethernet-based TCP/IP communication to exchange the endpoint information. What we now do is that we leverage the fact that we have our own daemon running on the system, which already knows how to reach remote nodes. And we use the network of daemons then to finally exchange the endpoint information, which is then used to establish the payload communication channel, which you see here below. And we already did some preliminary scaling results running simply an MPI initialization on a couple of nodes and up to 32 nodes and up to 1,536 ranks. And as you can see, if the so-called RMCOM interface is used, which is our interface to interact from the user level with the daemon, the relative time or execution time of the MPI init dramatically decreases. So that is basically the goal, that we want to further improve the startup times for really large scale MPI applications. When introducing the dMSA, I also introduced that we are thinking and working on integrating different hardware types than classical computer accelerator devices. So for example, quantum devices. And also here we would like to apply the dMSA approach. So that means we strive for integrating the QPU as a new module in the supercomputer, but we have a certain difference compared to classical compute resources. Since classical compute resources, we usually have, let's say, in the order of thousands of compute nodes, which can be assigned to jobs. But with respect to QPUs, we usually have, let's say, one QPU in the system, perhaps two or three, but that's it. So we have a scarce resource here. What we, of course, want to avoid is that we simply apply the exclusive scheduling, which is usually done in HPC, that a job can exclusively allocate such a device like a QPU, and the others are not able to access it, since usually you only put, let's say, requests from time to time to the QPU resources. On the other hand, what we also need to ensure is that if an HPC job, which also uses additional quantum resources, allocates those resources, that this job is guaranteed to receive its fair share of resources in order to not have too many idling resources when sending requests to the QPU. And therefore, we are currently working on a solution that enables us to implement a so-called mid-level scheduling, meaning that we have so-called quantum hybrid jobs, which allocate on the one hand classical HPC resources, but on the other hand also a share of the QPU resources. And we manage the QPU resources in terms of so-called virtual QPUs. That means when a job allocates quantum resources, it is assigned a certain share of the QPUs, and our solution will ensure that this share is provided to the job over time, so that we do not have any idling resources on the HPC side. But on the other hand, we also want to support with this solution the, let's say, classical quantum approach, meaning that people are still able to submit jobs via a cloud portal, where it's, let's say, where you do not have any timing guarantees when your request will be fulfilled. And therefore, we dedicate an additional cloud queue, which is then also served by our solution, the so-called PSQ-Sched, our backend scheduler. From the HPC point of view, in the Slurm world, we realized this as a kind of global resource, because the QPU can be basically used from any of the HPC nodes, and requests could come from any of the HPC nodes in the system, and therefore it doesn't really make sense to dedicate a certain partition to it. But we rather use the concept of so-called SLAM licenses as a global resource in order to ensure that the fair share of quantum resources is also assigned to the quantum hybrid jobs. The second part of, or the second component of ParaStation MPI is our MPI runtime library. As I mentioned before, it's an MPICH derivate. Currently, we have the MPICH 4.2.3 resources, and we are also working on integrating the most recent 4.3 resources, which are coming very soon. On the right-hand side, you can see the architecture diagram. In the left part of the picture, this is the MPICH stack. So going from the top to the bottom, we have the MPI applications on top of the MPI interface, which is standardized by the MPI standard. And below of that, we have the so-called MPIR layer, which covers all the hardware independent parts, for example, like collective algorithms, communicator handling, group handling, and so on. And below that, there is the ADI3 interface, so the abstract device interface. And this is where we hook in to the MPICH stack with our own so-called MPID or PSP device, which is implemented by using our own efficient low-level communication library, which is called PSCOM, which you see on the right-hand side. And PSCOM, in turn, is then able to leverage different underlying transports and protocols common in HPC, of course, starting from internode communication via efficient shared memory communication, but also, intranode communication, but also internode communication via UCX, and then in turns InfiniBand verbs, of course. And we also provide a solution for transparent network bridging. So if you remember what I told you about the idea of the cluster booster concept and also the network federation, this is our solution for transparent network federation in large-scale HPC systems, so that the PSCOM can transparently translate between the different protocols that it supports below. Of course, as we have developed the dMSA in the past years, our solution also provides different aspects of dMSA awareness. So the first thing to mention here is the support for so-called multi-level hierarchy aware collectives. If you're a bit familiar with collectives, what you usually do is that you have so-called SMP aware collectives, meaning that you try to minimize the internode communication if you're doing collective communication operations. So for example, a reduction operation would start that you first do the reduction within the computing nodes, and then only one of the processes on each of the nodes would then take part in the global reduction. And we adapt this concept to the next level as the dMSA introduces another layer in the hierarchy. And this allows us to then reduce the amount of communication that crosses module boundaries. Because the assumption is, of course, that if we have a computing system composed of different modules, that the inter-module communication traffic comes at a certain lower performance in terms of latency, but also throughput than the intra-module communication. Additionally, our communication stack offers extensions for accessing the modularity information from the application level. So what we, for example, introduce as a new communicator type, which can be used by the application to create communicators based on the module affinity. So if an application can make use of this information, then it would be able to create the communicator and know, okay, now I have a set of processes that is only running, for example, on the booster module. And finally, the MPI network bridging, which I already mentioned before, you can see it on the right-hand side by taking the example of bridging between the InfiniBand network on the one hand and the OmniPath network on the other hand. And as you can see, it is even transparent to our PSMPI communication stack. So the network translation really takes place below, only within the PSCOM communication library. And another aspect, what we are also working on, which also, let's say, affects all layers of the system software stack, meaning the process and resource management, the runtime library, and finally also the applications, is the aspect of malleability to further improve the utilization of the resources. So the motivation is really to further optimize system utilization by not only optimizing the mapping of assigned resources to the applications or workload at startup time, but even during runtime, since we might have applications which have different phases like pre-processing steps, post-processing steps, which require different resources compared to each other, and thereby also reducing the energy footprint. And what we want to achieve with that is to enable applications to dynamically add or remove resources during runtime, and thereby leveraging as far as possible the existing interfaces. And therefore, we exploit features which have been introduced with the MPI 4 standard in terms of the MPI sessions, and also make large use of mechanisms that have been standardized on the lower layer, namely the PMX layer, which is the interface that allows an MPI library to talk to the process management layer. Currently, we foresee two different usage models here. So one is the so-called active malleability. That means it is job initiated. So when the job itself knows, okay, now I need some more resources, or I would be able to release some resources to the system. And the second usage model is the so-called passive malleability, which is externally initiated. So for example, by the scheduling system. If the scheduling system, due to some input like priorities, but also perhaps based on input from the energy monitoring system, decides that a certain application or workload should release some resources to another application to improve the overall efficiency and utilization of the system, then according interfaces will be developed which allow us to interact with such mechanisms. Coming slowly to an end. So what is next from our side? We are currently extensively working on enabling the efficient execution of AI workloads on modular systems, so dynamically assigning the resources to the different phases and parts which belong to AI training, but also inference workloads, of course, leveraging the mechanisms such as malleability or the dMSA in general, as I mentioned before. In this context, of course, also the dynamic scheduling and resource management comes into play, which allows us then to dynamically reallocate resources during runtime in accordance with the current application mix, which is executed on the system. And finally, as mentioned also in my talk, we work on the efficient integration of quantum resources, which we aim for integrating as another module in a system, but a kind of special module, since the resource is a scarce module compared to the number of nodes that we see in the classical HPC world, and therefore rather it is rather integrated as kind of global resources with all the aspects that come with that. On my final slide, you see how the ParaStation components integrate within the EUPEX software stack. So we mark them here in orange, and as you can see, the ParaStation components are all scattered around the system level components of the EUPEX software stack. So we have the ParaStation health checker, which acts on the system level regarding monitoring and node health status. We have ParaStation MPI and also the resource management as part of the execution environment. And on the system management side, on the right-hand side, you can see the ParaStation cluster tools, which we aim to integrate with the Ocean software stack, which is also part of the EUPEX software stack, and so on. Yeah, so that was my overview on ParaStation Modulo and also the dynamic modular system architecture. And now I would be happy to take any questions. Thanks.
Thank you so much, Simon. for your participation to this webinar. It was really interesting to have an overview of what can be done with ParaStation Modulo Suite, and also to have insights of what you plan to develop for the future. So yeah, as Simon said, it's time for the Q&A. So please feel free to participate and to ask your question to our expert.
Pelazi, this is Angelus. Can I ask a question?
Of course, Angelus, go ahead.
Simon, thank you very much. A lot of information, right? A lot of stuff. Two quick questions. So for I/O, does ParaStation, do you rely on MPI I/O or do you do something special about it? Right? I don't know if.
Regarding the runtime library, we rely on what is provided by the MPIC sources. So as I showed here in this picture, we integrate below the ADI3 layer, but this mainly targets the efficient point-to-point communication. And for example, also the collective communication algorithms sit on top of that. And the same holds basically for the I/O, where we leverage what is provided in the MPIC stack.
Okay, all right, good. And then since you are at the lower level, I don't know, do you do anything about, or are you thinking about direct transfers, let's say from network to GPU or GPUs?
Yeah, that is also
system.
something that we support. You mean like direct communication transfers, like CUDA awareness in, for example, or GPU awareness in the communication? Is that what you mean?
Right,
Yes.
exactly. Without
Yes.
going through the host memory, right?
Yeah, exactly. No, that is something that is supported by our communication stack, and that we also further develop, of course. But there's no issue there. So you can use ParaStation MPI to have direct MPI communication transfers between GPU and GPU memory, GPU to CPU host memory, and so on and so forth.
Okay, great. Thank you very much, Simon. Thank you.
Yeah, you're welcome.
Do anyone else have a question for Simon? Okay, I personally have one. Did you develop some special feature for the EUPEX project in ParaStation?
In ParaStation, we had actually different aspects that were touched. So, for example, one very essential part is the connection establishment via the ParaStation daemon, which I mentioned before, so that we leverage our ParaStation daemons, which are already running on the compute nodes, for an accelerated MPI session startup in terms of a reduced time for the MPI init, to name only one of them. Then, of course, we have adapted our ticket suite to the needs of the early access program, and so on. So we have strived for integrating, let's say, different aspects, which were also coming from different privacy running projects, like the CA family of project, into the EUPEX software stack, in order to bring this into this Korean software stack that we intend to provide to the hosting sites.
Okay, thank you. No more questions? Oh, we got a question in the chat, maybe. From Matteo. Thank you, Simon. Very nice and neat presentation. About telemetry, do you use the management network to collect data?
Yes, that is also something that we support with the ParaStation daemons. So what we, for example, did is that the ParaStation daemons can be used for collecting accounting information, like energy accounting information on the node local nodes, and, for example, forward it to the central Slurm daemon, which then can present the accounting information to the user. The sampling frequency, I have to admit, that is something I currently do not know offhand, and if this even applies to all of the metrics that we currently collect. That is something I would need to double check with my colleagues.
Okay. So if we don't have more questions, we can stop the record here.
Mm-hmm.